Right now, as you hear this, a signal is arriving on Earth that left a small machine almost a full day ago. It has been travelling at the speed of light, the fastest that anything in the universe can move, for nearly 24 hours, and it has only just reached us. The machine that sent it is called Voyager 1. It is the most distant object human beings have ever built, more than 25 billion kilometres away, so far that its radio signal, crossing space at 300,000 kilometres every second, takes most of a day to reach the planet where it was made. The transmitter that produced that signal is weaker than the light bulb inside your refrigerator, and yet, across that impossible gulf, through the cold and the dark, we can still hear it. We have been listening for almost 50 years. Soon, we will stop. Not because we choose to, but because the machine is dying, slowly, the way all things eventually die. And one day in the near future, its voice will fade into the noise of the universe and never return. This is the story of that machine, where it came from, how it travelled so far, and what will become of it long after we can no longer hear it. Let us begin. The story does not begin with a rocket. It begins with a piece of arithmetic. In 1965, a doctoral student in aeronautics at the California Institute of Technology, working part-time at the Jet Propulsion Laboratory in Pasadena, was given a problem to study. His name was Gary Flandreau. His task was to look for ways to send a spacecraft to the outer planets, the giant worlds beyond Mars, which at the time no spacecraft had ever visited. The problem was distance. The outer planets are so far away that a direct flight, using the rockets of the era, would take 30 or 40 years. A mission like that was not practical. No one wanted to launch a spacecraft that the engineers who built it might not live to see arrive. So Flandreau did something simple. He plotted where the outer planets would be in the coming decades. He drew their positions on paper year by year, and he looked for a pattern, and he found one. What Flandreau discovered was that Jupiter, Saturn, Uranus, and Neptune were drifting into a rare arrangement. By the late 1970s, all 4 giant planets would be lined up along the same broad arc of the solar system, strung out on the same side of the Sun. This alignment is not common. The 4 outer planets fall into this particular configuration only once every 176 years. The last time it had happened, Thomas Jefferson was President of the United States. And the arrangement made something remarkable possible. A single spacecraft, launched at the right moment, could fly past Jupiter and then use Jupiter's enormous gravity to slingshot itself onward to Saturn, and then onward again to Uranus, and then to Neptune. Each planet would whip the spacecraft forward, adding speed, bending its path toward the next world in line. The technique is called a gravity assist. The spacecraft steals a tiny amount of the planet's orbital motion and uses it to accelerate. The planet slows down by an immeasurably small amount. The spacecraft speeds up enormously. Flandreau calculated that with these repeated gravity assists, a journey that would otherwise take 30 or 40 years could be completed in about 12. The catch was the timing. To catch the alignment, the spacecraft had to launch in 1977. Miss that window, and the opportunity would not return for another century and 3/4. NASA called the idea the Grand Tour. The original plan was ambitious: 4 spacecraft exploring all of the outer planets in 2 pairs. But the late 1960s and early 1970s were a difficult time for the American space program. After the moon landings, budgets were cut. The money was needed for the space shuttle. The Grand Tour was scaled back and back again, until what survived was a smaller mission of just 2 spacecraft. 2 probes where there had been 4. That was the compromise. The 2 spacecraft were named Voyager 1 and Voyager 2. They were built to be identical, and they were built to be redundant, so that if one failed, the other could still complete the mission. And onto each of them, the engineers fixed something that had nothing to do with science at all. A phonograph record, made of gold-plated copper, sealed in an aluminum case. It was called the Golden Record, and we will return to what it contains and why it is there later in this story. For now, it is enough to know that each Voyager carried bolted to its side, a message. A small, deliberate attempt to say, to whatever might one day find it, that we existed. Voyager 2 launched first, on the 20th of August 1977, on a slower path that would let it reach all 4 outer planets. Voyager 1 followed 2 weeks later, on the 5th of September, on a faster trajectory aimed at Jupiter and Saturn. Despite launching second, Voyager 1 was moving quickly enough that it overtook its twin before the end of the year. The 2 machines, built in the same clean rooms by the same hands, set off in slightly different directions, toward the same distant frontier. Before we go further, if you are kind enough, a gentle like and tap on subscribe would mean the world to me. It is a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive. What they found when they reached the outer planets rewrote the textbooks. At Jupiter, Voyager 1 captured the first close images of the largest planet in the solar system, its bands of cloud and its great storm. It discovered a thin ring around the planet that no one had known was there, and 2 small moons. And when it looked at Jupiter's moon Io, it saw something nobody had expected. Volcanoes. Active volcanoes, erupting plumes of material hundreds of kilometers into space. It was the first time anyone had ever seen active volcanic eruptions on a world other than Earth. At Saturn, the spacecraft found 5 new moons and a faint additional ring. Then Saturn's gravity swung Voyager 1 upward, out of the flat plane in which the planets orbit, and sent it climbing toward the edge of the solar system. Voyager 2 continued on the longer path, and over the following years it did something that has still never been repeated. It flew past Uranus, and then past Neptune, becoming the first and so far the only spacecraft ever to visit those 2 worlds. Between them, the 2 Voyagers gave humanity its first close look at the entire outer solar system. Everything we know about those planets as real places, rather than points of light, began with these 2 machines. And then, in 1990, with its planetary work finished and Voyager 1 climbing out into the dark, the astronomer Carl Sagan, who had helped create the Golden Record, persuaded NASA to do one last thing with the spacecraft's camera before it was shut down to save power. He asked them to turn the camera around, to point it back across the entire solar system toward home and take a photograph. The image that came back is one of the most famous ever taken. From a distance of about 6 billion kilometers, the Earth appears as a single point of light, less than a pixel across, a pale blue dot suspended in a beam of scattered sunlight. Everyone who has ever lived, every empire, every war, every person you have ever known or loved, all of it, on that one tiny point in an ocean of black. Sagan would later write about what that image meant, that our planet is a lonely speck in the great enveloping cosmic dark, that there is, perhaps, no better demonstration of the folly of human conceit than this distant image of our tiny world. After that, the cameras were switched off. There was nothing left to photograph that the spacecraft's failing power could justify, and the Voyagers were now headed somewhere no camera was needed. They were leaving, moving outward through the outermost reaches of the Sun's influence, toward the boundary where the solar system ends and interstellar space begins. That boundary has a name. It is called the heliopause, the place where the constant wind of particles streaming off the Sun finally becomes too weak to push back the thin gas that fills the space between the stars. On the 25th of August, 2012, Voyager 1 crossed it. For the first time in history, a human-made object had left the bubble of the Sun's influence entirely and entered the space between the stars. Voyager 2 followed, through a different part of the boundary, in November of 2018. 2 small machines, built in the 1970s, designed to last 5 years, had become the first emissaries from Earth to cross into the wider galaxy. They are still out there, still moving outward at roughly 17 kilometers every second, a speed that will never decrease, because there is nothing in the emptiness ahead to slow them down. And they are still, against every reasonable expectation, talking to us. Nearly 50 years after they launched, with transmitters weaker than household light bulbs, from distances so vast that their signals take almost a full day to arrive, the Voyagers are still sending data back to Earth. Which raises a question that sounds simple and is not. How? How is it possible to hear a whisper that faint from a machine that far away, when the signal arriving on Earth is so weak it can barely be distinguished from the background hum of the universe itself? The answer involves some of the most extraordinary engineering ever attempted, a network of giant antennas spread across the planet, and a small team of people who have spent their careers keeping a connection alive across the void. That is where this story goes next. The answer begins with a number so small it is almost meaningless to write down. By the time a signal from Voyager 1 reaches the Earth, after travelling for nearly a full day across 25 billion kilometres of empty space, it arrives carrying a power of less than 1 attawatt. An attawatt is a billionth of a single watt. To put that in some kind of perspective, the signal reaching Earth from Voyager is roughly 20 billion times weaker than the power stored in the battery of a digital wristwatch. By any ordinary standard, it is not there at all. It is a whisper so faint that it is nearly indistinguishable from the background hum of the universe itself, the dim electromagnetic noise that fills all of space. And yet, every day, we find it. We pull that whisper out of the noise, decode it, and read what the spacecraft has to say. How we do that is one of the quietest triumphs of human engineering. Consider what Voyager has to work with. Bolted to the spacecraft is a dish antenna 3.7 meters across, a little under 12 feet. Behind that dish sits a transmitter, and the transmitter runs on roughly the same amount of power as the light bulb inside a household refrigerator, about 20 watts. That is all it has ever had. There is no way to make the signal stronger. The spacecraft simply points its dish back toward the Earth, transmits as loudly as its small power allows, and trusts that someone, across all those billions of kilometers, is listening carefully enough to hear. Someone is. To catch that whisper, NASA built one of the most remarkable instruments in the world. It is called the Deep Space Network, and it consists of 3 enormous antenna complexes spaced around the planet. One sits in the high desert of Goldstone in California. One stands outside Madrid in Spain. The third is near Canberra in Australia. The 3 sites are positioned at roughly equal distances apart, about a third of the way around the globe from one another. The reason for that spacing is simple and elegant. The Earth rotates. As it turns, any single antenna will eventually swing away from the part of the sky where a spacecraft sits, losing the line of sight. But with 3 complexes spaced evenly around the planet, as one rotates out of view, another rotates into it. There is always at least one dish facing the right part of the sky. The network never loses sight of the spacecraft it is tracking, because the planet itself can never turn far enough to hide them all at once. The largest antennas in the network are 70 meters across, parabolic dishes as tall as a 20-story building. Their vast, curved surfaces gather the faint radio waves arriving from deep space and focus all of them onto a single, exquisitely sensitive receiver. And those receivers are kept astonishingly cold, chilled to just a few degrees above absolute zero, the lowest temperature physically possible. The reason is that warmth, any warmth at all, produces electronic noise. Even the faint heat of the receiver's own components, if they were left at room temperature, would generate enough static to drown out Voyager's whisper completely. To hear something that faint, the instrument listening for it must be made almost perfectly silent. And in the language of electronics, silence means cold. Even then, the task is not simple. Because Voyager is racing away from us at enormous speed, the frequency of its signal is shifted, stretched out, by the same effect that reddens the light of distant galaxies. The signal does not arrive quite where you would expect to find it, and the exact amount it has shifted drifts as the spacecraft moves and as the Earth turns. The engineers tracking it have to calculate and correct for that shift continuously, in real time, simply to keep the signal in focus long enough to read it. And then there is the distance itself, which imposes a kind of slowness on the entire conversation. A command sent from Earth to Voyager 1 takes almost a full day to arrive. The spacecraft's response takes almost a full day to come back. One of the engineers who works on the mission described what that means in practice. If she sends a command to the spacecraft on a Monday morning, she sees the effect of that command on Wednesday. Every instruction, every question, every adjustment is separated from its answer by the better part of 2 days. There is no conversation in real time. There is only sending and waiting and listening. That is how we listen. Talking back is, in one sense, easier. The same giant dishes that listen can also transmit, and when they do, they can pour far more power into the signal than Voyager ever could. The command signal that Earth sends out to the spacecraft is more than 1,000 times stronger than the faint reply that comes back. From Voyager's side, Earth is the loud one. We shout across the solar system, and the spacecraft answers in a whisper. But the deepest problem is not distance, it is power and time. Voyager does not run on sunlight. Out where it is, the sun is just another bright star, far too distant to power anything. Instead, each spacecraft carries 3 radioisotope thermoelectric generators, devices that produce electricity from the heat of slowly decaying plutonium. When the Voyagers launched, each one generated about 470 watts of power. But plutonium decays. A little more of it turns to other elements every year, and the heat it produces, and the electricity that heat generates, steadily diminishes. Today, after nearly 5 decades, each spacecraft has only around 210 watts left, less than half of what it began with, and the decline never stops. This slow loss of power forces a quiet, ongoing series of sacrifices. Each Voyager launched carrying 10 or 11 scientific instruments. Most have already been switched off. The cameras were shut down back in 1990 after the pale blue dot because there was nothing left to photograph and the power they used was needed elsewhere. In the years since, one instrument after another has been turned off to conserve what little electricity remains. In early 2025, engineers shut down the instrument that had helped confirm exactly when Voyager 1 crossed into interstellar space. Today, only a handful of instruments are still running on each spacecraft, and roughly once a year, the team must choose another one to switch off. They are deciding, one by one, which senses to take away from a machine that is still working, still reporting, still alive, but that can no longer afford to do everything it once could. What makes all of this stranger is how little the spacecraft has to think with. The combined memory of all of Voyager's computers is about 68 kilobytes. That is less than a single modern photograph would require, less than the electronic key to a car. The phone in your pocket has millions of times more processing power than the machine we are still flying at the edge of the solar system. And yet, for nearly 50 years, engineers have been sending software updates to these computers, patching errors, working around broken hardware, rewriting the spacecraft's instructions from billions of kilometers away on machines they will never touch again. Keeping these machines alive has not been smooth. Several times we have very nearly lost them. The first crisis came early. In 1978, less than a year after launch, a scheduling mistake on the ground meant that Voyager 2 did not hear from Earth for 7 days. The spacecraft's software interpreted the silence as a failure of its primary radio receiver and switched to its backup. But the backup receiver had a broken component and could not properly lock onto the signal from Earth. When engineers forced the spacecraft back to the primary receiver, its fuses blew and the primary receiver died completely. Voyager 2 was now stranded, 8 months into a mission meant to last more than a decade, dependent entirely on a backup receiver that did not work correctly. The engineers found a way. They began transmitting test signals, slowly sweeping across a range of frequencies, searching for the precise setting that the damaged receiver could still detect. After hours of trying, the spacecraft answered. And that workaround, improvised in 1978, is how Voyager 2 has communicated with Earth ever since. For nearly 5 decades, on a receiver that has been broken since before most people alive today were born. The crises continued as the spacecraft aged. In January of 2020, Voyager 2 performed a routine maneuver, but a delay in its commands left two power-hungry systems running at the same time, drawing more electricity than the spacecraft could provide. Its protective software instantly shut down all of its remaining science instruments to prevent a catastrophic failure. It took a week to bring them back, slowed by the 17-hour delay each way. In 2022, Voyager 1 began sending back data that made no sense, a stream of meaningless noise where there should have been readings. Engineers eventually traced the problem to a small onboard computer that had failed years earlier. The spacecraft had begun routing its data through the dead machine, which was garbling everything before it was transmitted. The fix was to tell it to stop using the broken computer. And then, in 2023, Voyager 2 fell silent. For 2 weeks it sent nothing and received nothing. A command had accidentally tilted its antenna slightly away from the Earth, by only 2 degrees, but 2 degrees across that distance was enough to break the connection completely. The situation was made worse by the fact that Voyager 2, travelling south out of the solar system, can only be reached by the single Deep Space Network station in Australia. For 2 weeks, there was only silence. And then, faintly, a signal, a kind of heartbeat, confirming the spacecraft was at least still functioning. The next day, the team did something dramatic. They aimed the most powerful transmitter they had at the spacecraft's position, raised the signal to the highest power available, and sent a single command shouted across the entire solar system, an instruction telling Voyager 2 to turn its antenna back toward Earth. The command had a low chance of reaching home, but it worked. The antenna swung back into alignment, and the connection was restored. Behind every one of these rescues is a small group of people. The team that keeps both Voyagers alive numbers only about 10. 10 people, many of whom have spent the better part of their careers on this single mission, are responsible for maintaining contact with the two most distant objects humanity has ever made. Every time something has broken, across nearly 50 years, this small team has found a way to keep the machines talking. The result has been the same every time. The Voyagers are still there, and they are still speaking. But this cannot continue forever. The power is running out. The instruments are going dark, one by one. And there is a date, not far away, after which there will be nothing left to switch off, and the last signal will fade, and the silence will become permanent. What happens to the Voyagers then, after we can no longer hear them, is the final part of this story. The end, when it comes, will not be dramatic. There will be no explosion, no final transmission of historic words, no single moment of failure that makes the news. It will simply be a fading. The power on each spacecraft drops a little more every year, and the team has already switched off nearly everything that can be switched off. The cameras are gone, most of the instruments are gone. Each year, another sensor is turned off to keep the essential systems running a little longer. The engineers who manage the mission have spoken about their hopes with a kind of careful honesty. They would like to reach the 50th anniversary of the launches in 2027. They believe they may be able to keep at least one instrument running into the 2030s, but not much longer than that. At some point, there will not be enough power left to run even a single instrument, or to keep the transmitter warm enough to send a signal home. And on that day, or someday soon after, the last faint whisper from Voyager will arrive at the Earth, be recorded, and not be followed by another. The connection that has lasted nearly half a century will end, not with a failure, with a silence. There is a moment coming, before that silence, that marks how far these machines have travelled. In November of 2026, Voyager 1 will reach a distance of 1 light day from Earth. It will become the first object ever built by human hands to be so far away that its signal, travelling at the fastest speed the universe permits, takes a full 24 hours to reach us. A full day of travel, just to cross the gap between the Earth and a machine we launched within living memory. It is a milestone with no practical importance. The spacecraft does nothing different when it crosses that invisible line. But it is a measure of something, of how far a small, patient effort can reach, given enough time, and of how far away these machines will be when we finally lose them. And here is the strange and important fact at the centre of this story. When the signal fades, the Voyagers do not stop. They do not slow down. They do not fall. There is nothing out there to slow them or to pull them off course. The same emptiness that makes them so hard to hear also means that nothing stands in their way. When the last instrument is switched off and the transmitter goes cold and we can no longer hear them, the two spacecraft will keep moving outward at 17 kilometers every second, exactly as they have for 50 years. They will simply do it in silence and in the dark, with no one listening. The mission will end, the journey will not. Which brings us, at last, to the object bolted to the side of each spacecraft, the one that has nothing to do with science, the golden record. When the Voyagers were being built, a small group of people understood something about what these machines would become. They understood that the probes would, eventually, outlast their mission, that they would keep flying long after the last signal, into a future too distant to picture. And so they decided to send something with them. Not data, not instruments, a message, a record of who we were, in case anything ever found it. The project was led by the astronomer Carl Sagan of Cornell University, who assembled a small committee to decide what humanity should say to the cosmos. It included the scientist Frank Drake, the writer Anne Druyan, the science journalist Timothy Ferris, and the artist John Lomberg. They were given less than a year and an almost impossible task: to compress all of human life, all of its sound and image and feeling, onto a single phonograph record made of gold-plated copper that might drift through space for longer than the human species itself would exist. Every choice they made was a choice about what mattered. What, out of everything our species had ever done, deserved to be the thing that survived? What they chose is a portrait of Earth assembled with extraordinary care. The record holds 116 images, encoded so that they can be reconstructed by anyone who works out how to read them. Photographs of people, of landscapes, of animals, of how we eat and build and live. It holds greetings spoken in 55 different languages, ancient and modern. It holds a 12-minute sequence of the sounds of Earth, surf and wind and thunder, the calls of birds, the songs of whales. And it holds about 90 minutes of music, 27 pieces chosen to represent the whole of human culture. There is Bach and Mozart and Beethoven. There is a blues recording by Blind Willie Johnson. There is classical music from China and folk music from Bulgaria. And there is, famously, a rock and roll song, Chuck Berry's Johnny Be Good. When some on the committee objected that rock and roll was adolescent, Sagan replied that there are a lot of adolescents on the planet. They had hoped to include a song by the Beatles as well, but the record company that held the rights declined to give permission. The most distant human object in existence very nearly carried the Beatles into interstellar space, and does not, because of a copyright decision made in 1977. There is one more thing on the record, stranger and more intimate than the rest. During the project, Anne Druyan, the creative director, recorded an hour of her own brainwaves, her neural activity, as she lay still and thought about a series of subjects: the history of the Earth, human civilization, and, as it happened, a person she had recently fallen in love with, who was Carl Sagan himself. The two would later marry. Encoded onto the record, somewhere in that hour of electrical activity, is the trace of a human mind thinking about love. It is sealed in gold, on a spacecraft, drifting out of the solar system, and it will still be there, exactly as it was that day, when everyone who knew either of them has been gone for millions of years. On the cover of the record, etched into the metal, is a kind of map. It shows the position of the Sun relative to 14 pulsars, rapidly spinning stars that each flash with a precise and unique rhythm. The idea is that any civilization advanced enough to find the record could use those pulsars, like landmarks, to work out where the spacecraft came from and roughly when it was launched. It is, in effect, a return address, a set of directions back to a small blue planet, left for whoever might one day wonder where this object came from. Sagan understood how unlikely it was that anyone would ever find it. The chance, he knew, was for all practical purposes zero. But that, he felt, was not really the point. The launching of this bottle into the cosmic ocean, he said, says something very hopeful about life on this planet. Because the truth is that the Golden Record was never really a message to aliens. It was a message about us, and in some ways, it was a message to ourselves. A statement that we had existed, that we had been here, that for a brief moment on a small world, we had looked up and tried to say something to the dark. The records are built to last. In the vacuum of interstellar space, there is almost nothing to wear them away. No air, no water, no weather. The gold plating will protect the grooves from the slow erosion of interstellar dust. Scientists estimate that the records could remain intact and readable for billions of years, which means something that is genuinely difficult to hold in the mind. The Voyager records will almost certainly outlast the Earth itself. In roughly 5 billion years, the Sun will reach the end of its life. It will swell into a red giant, expanding outward, swallowing Mercury, then Venus, and very likely the Earth, scorching away the oceans and the air and every last trace of everything that ever lived here. The planet that built the Voyagers will be gone, but the Voyagers will still be out there. The two small machines, and the golden records fixed to their sides, will still be drifting through the galaxy, carrying the sounds and images of a world that no longer exists. Neither spacecraft is aimed at any particular star. They are not going anywhere in the sense of having a destination. They are simply leaving. But the galaxy is full of stars, and over enough time, the Voyagers will drift near some of them. In about 40,000 years, Voyager 1 will pass within roughly 1.5 light-years of a small star called Gliese 445. Around the same time, Voyager 2 will pass at a similar distance from another star called Ross 248. Neither spacecraft will enter those star systems. Neither will be captured or slow down or land. They will simply pass by, in the dark, light-years away, two artifacts from a vanished world drifting silently through skies that are not ours. And then they will continue on, toward the spaces between the next stars and the stars after those. What happens beyond that, we can only estimate. The Voyagers, like the Sun, like every star you have ever seen, are in orbit around the centre of the Milky Way. They will circle the galaxy slowly, taking hundreds of millions of years to complete a single loop, rising and falling through the disk of stars for as long as the galaxy itself endures. They may drift for billions of years. They may, in some unimaginably distant future, be found by something we cannot begin to picture. Far more likely, they will never be found at all, and will simply continue, intact and silent, long after the Earth and the Sun, and perhaps even the memory of the human story itself, have ended. It is worth sitting for a moment with what this mission actually was. Human beings have existed, in something like our current form, for a few 100,000 years. We have had written language for perhaps 5,000. We have been able to leave the surface of our own planet for less than 70. And in that last sliver of time, almost as soon as it became possible, we built two machines, attached to each of them a record of who we were, and sent them out of the solar system with no expectation of return and almost no chance of ever being found. There was no practical reason to include the golden record. It added nothing to the science. It was, in the most literal sense, a message in a bottle, thrown into an ocean so vast that the bottle will likely never wash up on any shore. And we did it anyway. Something in us needed to do it. The same impulse that carves names into stone, that paints hands on cave walls, that builds monuments meant to outlast the people who build them, reached its furthest expression in two spacecraft now leaving the solar system in opposite directions. We are a species that has always wanted to be remembered. The Voyagers are the longest reach of that wanting. They are the part of us most likely to still exist when there is nothing else of us left at all. And there is something both humbling and strangely comforting in that. That whatever happens to us, here, on this small and temporary world, some trace of what we were will go on, in the dark, for a very long time. For now, though, they are still here. Still close enough, in cosmic terms, to hear. Two machines built in the 1970s by people who mostly did not expect them to last. Designed for 5 years, now approaching 50, still moving outward, still, for a little while longer, speaking to us across the dark. Soon the last signal will come, and we will not know at the time that it is the last. There will be no warning from the spacecraft. Just one more faint transmission, like all the others, arriving after a day of travel, recorded and never followed by another. And after that, the Voyagers will belong entirely to the silence and the dark, carrying their golden records and the trace of a mind thinking about love and the songs of whales and a rock and roll song outward forever on behalf of everyone who has ever lived. We made something that will outlast us. We pointed it toward the stars, and we told it to keep going. And it will. Long after we are gone, from a small world that will not always be here, 2 machines will still be carrying the story of what it was like to be alive on the day that we let them go.